In this short session, I will explain a few items with regard to properties of composite materials. Composite materials are composed of different constituents. Fiber-reinforced polymers are made of fibers and polymers. Hybrids have an additional constituent, metal sheets. In this lecture, I will focus on fiber-reinforced polymers with continuous fibers. Some properties of fiber-reinforced polymers can be estimated by a simple rule of mixtures. This approach is applicable for the density of the composite and for the strength and stiffness of the composite. For other properties, like failure strain of compressive properties, you should not use this estimation. And realize it is an estimation. So if it gives a first approximation of values. To start with the density, the rule of mixtures is applied as follows. The total mass of the composite is the sum of the mass of the fibers and the mass of the polymer we put in the composite. Making a composite in the lab or factory, we do that by weighing of the constituents. If we rewrite the mass as a product of density and volume, we get the second formula. Realize that we assume a perfect mixture, so no voids nor porosity are inside the composite. Next, we can divide both sides of the equation by the volume of the composite and we get weight fractions, represented in the fourth formula by the small letter. In the given ideal case, the sum of both fractions should be equal to 1. We now have a simple linear equation for the density. If we use this equation for a specific composite, here a glass fiber epoxy, we see that the composite density is a linear function of the fiber volume fraction. I use the fiber volume fraction because we often use this parameter in our analysis and calculations. If there are no fibers in a composite, when it is a pure polymer, the density is equal to the density of the polymer. In this example, about 1200 kilos per cubic meter. If there was no polymer in a composite, the density would be equal to the density of the glass fibers, which is about 2,500 kilos per cubic meter. For all other ratios, the line or equation can help to find a first indication of the composite density. Note that most composites with short, long and continuous fibers have a fiber volume content in the range of 0.2 to 0.6 or between 20 and 60%. This approach can also be used to approximate some mechanical properties, like the E modulus under tension. I will show this for carbon fiber epoxy composites. In this example, the fibers are continuous and the composite is made from unidirectional materials. Looking at the line for the UD material, it is similar to the line for the density. When there are no fibers, the fiber volume fraction is 0 and the E modulus is equal to the E modulus of the polymer, which is about 4 to 5 gigapascal. When the composite would consist of 100% fibers, the E modulus is equal to the modulus of the fibers, which is close to 250 gigapascal. For fiber volume contents between 0 and 1 or 0 and 100%, the modulus can be found by the formula or the plot. Most high-performance composites have fiber volume fractions in the range of 45 to 60%, the shaded area. If you make a cross-ply composite, 50% of the fibers are in 0 direction and 50% in orthogonal direction. Then the E modulus is roughly divided by 2. For each fiber volume content. Note that the UD material has a very low E modulus in transverse direction, equal to the modulus of the polymer. If we go one step further and look at the so-called quasi-isotropic laminate, consisting of fibers in 0, 90 and plus or minus 45 degree directions, the E modulus is further reduced and is even lower than the E modulus of aluminum, which is also indicated in the plot. This shows that a nice and elegant rule is available for a first estimate of some properties, but always analyze first whether this rule is applicable. To finish this session, I would like to show briefly some other properties of composite materials, which are often used for structural applications. In this table, you see the 3 main fiber types for structural aerospace applications: glass, carbon and aramid fibers. Also the hybrid material, fiber metal laminates, is mentioned. Noteworthy in this table are, first, the low failure strain of the carbon fibers, which is close to 1%. This might be a point of extra attention when designing and manufacturing with these fibers. Second, carbon fibers and fiber metal laminates are good electrical conductors. For fiber metal laminates, this is caused by the aluminum layers. These metal layers also play a positive role in the flame resistance, resistance to ultraviolet radiation, and resistance to chemicals. Most of the properties in the table can be easily explained when the composition and structure of the composite is well understood.